But yeah, this session is going to be about image filters and custom fragment shaders. I will be sharing a lot of demos, and there will be multiple live coding sessions as well within. So feel free to start a project right now if you would like to. And I'm just going to go ahead and start with something I saw 2 weeks ago. I'm not sure how many of you follow Luke, but I'm pretty sure at least one or two of you follows Marcus Brownlee. So I used to watch him a lot. He does a lot of tech reviews about a lot of products, and I trust his reviews. They are high quality. And he announced a product which is for the first time is a software. So I wanted to check it out, and then I wanted to check it out more because it was created with Compose multi-platform, and it's new to me. I have heard quite a lot of things about it because it was a copy paste from Flutter. I wanted to know why. And then I got into the app, and I really loved it. There was one issue, which is the blur. So on iOS, when I looked at the app, it had really nice blur. If you can see it here on the right side, on iOS, they have the blur that is blurring a section of the background. But the thing that got my attention about it was how it blends really nicely at the edges. It's not like a hard cut. On Android, obviously, it doesn't work at all because Android for so many years does not have support for blur. Even though with Compose multi-platform, they have a library called Haze, which allows them to do something like blurring that we already are used to in Flutter. But that aside, the reason I wanted to show you this is one other thing that reminds us of how the two, even though like this is the same UI, how it looks totally different from one platform to the other, and how most of the time iOS gets the higher quality whenever when we are talking about UI or care about the details. And this issue reminds me of exactly something else that I have seen a few years ago, which makes into a good transition into the same problem, which is the difference between iOS and Android. This image here, or this video that's playing here, is on the Flutter documentation. It describes the difference between what happens at the edge of scrolling on iOS and on Android. On iOS, you're scrolling and then you are at the end, and then you have this over scroll effect where it just allows you to scroll into the void for as much as possible. Obviously, then it will have to go back nicely and bounce back very nicely. But on Android, we have this really ugly thing at the top, which is the glowing thing. For many years, that was the case, but finally, Android have decided to get their designers to do something about it, and they have this new stretch effect. So at the edge, instead of showing the glowing effect, they just stretch the content of whatever is inside the scrolling view, and it looks very nice. It simulates the physics of stretching as well. And once I saw that, probably the same day or the same week, I don't remember exactly, I went to the Flutter GitHub repo, and they wanted to mention this to the team so that they can work on it. And naively enough, I gave them a solution. I was like, oh yeah, just update the padding and make the size and increase the size and all that. But it turned out that wasn't all of it, but maybe after like 6 or 8 months, they ended up making an implementation that looks like this. So now if you are on Android, one of the latest versions, and you're using Flutter, obviously, it will do the stretching effect instead of the glowing one, which is still also existing in anything that is not Material 3. So this is only when Material 3 is enabled, by the way. Yet, this seems to be a fix to the problem. The issue is still open, even as of today. The issue has not been closed. Why? Why is that? Well, we need to compare it with the native Android implementation and how it looks like versus how the correct one is doing it. So the current one in Flutter, and then there is the correct one here on the right side. It might be a little bit hard for you to see the difference, so we'll describe it to you. one is obviously feels much better, but the current one in Flutter does what we call a uniform transformation. So it takes all the pixels within the view and it stretches them all with the same value. So they are all stretching, even if you are at the top or at the bottom, everything is stretching within the same values. But the correct implementation that is on Android, it stretches a lot at the top and it stretches a little at the bottom. So it seems to be like a progressive in a way that the more we are closer to the anchor point, which is where we start the scrolling over scrolling from, the scrolling effect gets lower and lower, the stretching effect starts to become lower and lower. So this is a higher quality image just to describe the difference so that you can tell. Sorry, this is one of those issues where if you see it, you cannot unsee it. You will now see it everywhere. You want to see, you can't tell whether this is a Flutter app or not a Flutter app. Obviously, you need to see the real, the one on Android so that you can feel the difference. But yeah, it is one of those issues. The Flutter team replied, they said, okay, now we have an implementation, but to create something that looks exactly like the Android one, we need custom shaders, and that was 2021. I really did not know what that is. So that was how I got introduced to the idea of shaders in the beginning. The issue is now still open. They just have renamed it to re-implement the effect using custom scrolling using shaders. So now we know that these shaders are going to fix a problem that is very clear to us, that we can see with in our day-to-day life as developers. So let's give them a proper introduction. Between all of these, a native app, web app, Flutter game, React Native, or operating system, there is one thing in common. Everything runs on a screen. And that's the thing that Flutter says. We are pushing pixels into the screen. So if we take a look at any screen and we dive deep into it, we see that the screen is just a bunch of physical pixels or physical lights that they will get different values, and based on these different values it will render a final color. That color is what we see. So it doesn't matter if it is a nice rounded button or just a simple text. In the end, it's just a pixel. So let's see how does the GPU in the end, how does the GPU take something from being described in code, or let's say just described in literally in pixels, how does it take it and transform it into something onto the physical device. For that, there is something called the GPU pipeline. It takes a bunch of vertex specs, which is positions, vertexes, or textures, like multiples of them. So for us, for now, we want to draw a simple rectangle, and we send it a triangle, sorry, and then we want to send it these values to describe it. We will have a point in time. So we send them at the beginning. They are the first input there, but then we get the vertex shader, which is the place where we get to modify them if we want to modify or transform the way they look, or make them bigger, or do any other kind of transformations to them. So this is a place where we can modify them. Then tessellation, which is done optionally by the GPU in order to take all of these points and put them into primitives, that these primitives can be easily drawn by the GPU. But then we get one other chance where we can modify this geometry that was produced by the tessellation step, and here we get to to transform those primitives into other primitives. For example, if we want to optimize, but the primitives are mostly other triangles. This is the most basic shape in GPU programming that could be drawn, and it's not just one line. And then rasterization, which decides which are the pixels that will be covered by this, and then we give them colors. So if we decide what are the pixels, and then finally we're going to have to give them a color, and that's where the fragment shaders comes in. And then the final value is going to be a buffer that will be straight away taken to the GPU and be drawn as a picture. Obviously, as you can see, this is an ugly triangle, not the one we wanted to do, but if we put things to perspective, this is just how we are looking at it from very, very close. If we take it a little bit back, and then put it on a screen, it actually is just a triangle. Just scale it back again, and it is just actually a triangle in the end. So we were just looking at it very closely. So we have seen few of these shaders. The word shader replied multiple times, but whenever we mention it, it's a phase where we can modify the output of the previous phase. So we are doing some sort of programming. So a shader is a program. It runs on the GPU. That is the main difference between it and something else, because running something on the GPU, we're going to have to follow the rules and the laws of the GPU. And a fragment shader is a program that's responsible for determining the final color. So as we have seen before, the final step here when we are looking at the fragment shader, we just changing the color. So fragment shader just takes position or whatever kind of other input, but its final goal is to decide the final color of that fragment of a pixel or just the pixel itself. So now we have an idea of what is a fragment shader, how does it relate to Flutter. Obviously, as I said in the beginning, it doesn't matter if it is Flutter or React Native or anything else, everything has to go through this. And this pipeline here is the way Flutter renders, like you'd go through the build and then the layout phase and then finally the paint phase. So the paint phase is obviously almost the point before we send anything to the GPU, which is when we do the composition as a final point. But at painting, we are done with almost anything that is expensive in Flutter, like building and layout. That's why we don't want to do a lot of rebuilding, because sometimes it gets expensive. Layout is also very expensive, but paint is, we are talking about low-level APIs, very low-level APIs that we are calling. So here at the we hook into the painting level, and then we give it fragment shaders, and those are the ones that we'll be talking about today as well. So I'm going to give you a couple of examples of where these fragment shaders are used in the framework. You might think that they are very specific, but they're everywhere. So anywhere you draw in, for example, a container that draws a color, a very simple color, in the end, it will end up using something like solid fill, which is a fragment shader that just does one thing. It takes a color as an input, and that is the color that will be produced in the end. A gradient is another very good example. So all gradients, whether it's linear, whether it's radial, whether it's sweep gradient, all of them are also fragment shaders. Another one is not very low level. It's something also introduced with Android 12 just in 2021. So do you guys remember when we used to click on a button on iOS, on Android, there was a ripple effect, which is just one circle becoming bigger and bigger until it fills the entire possible area. With Android 12 and afterwards, there is a new effect, which is the ink sparkle. So instead of doing the ripple, there's something like sand, but it is noisy, so it's not uniform. So the noise that is generated is very much random, but it feels much more physical, or feels much more close to what a physical feedback effect looks like. So this is not very high quality, but you can obviously try to do this in Flutter and see the effect for yourself, because on Android 12 and afterwards, this is enabled by default. So we have seen examples where this is being used as a core feature, like drawing a color or drawing a gradient, and also high-level features like using ink sparkle to draw something totally not as simple as a color. And then there is the other one, which is the blur effect. So blur effect is a little bit more complicated. Here I'm showing you the example of something called direct blur, and it has nothing to do with the blur that we are showing you right here. That blur is just an image filter that is applied on this image here. But we are at the point where we have seen that how we can relate to this. So we have seen that we have an image that is being blurred, and the way it's being blurred is using fragment shaders as well. So now we know that these shaders are gonna allow us to do a little bit more transformations. So if you remember the first problem that we have seen, or sorry, the second problem, we were updating the content when we are scrolling, overstretching, we were trying to do some sort of transformation. So we were transforming something that's already existing, not like the cases where we have seen in the last two cases, which is here creating new content. This one is also producing new content. All of these are producing new content, while this one, blur, is transforming the content of something else. So with that, let's take a look at the current API for image filters, because now we know that they will take us where we want, or at least very close to that. The ways we usually use them is using a backdrop filter or an image filtered. So both of these are widgets that allow us to access the image filters API straight away. Image filter or image filtered, you just have a widget and then you apply the filter on top of it. They have this very clear documentation about it, where they say applying the filter and not giving it any value doesn't mean the filter is not going to be applied. So this is just kind of a performance nitpick, but very much important if you are trying to do tiny optimizations here and there. So for image filtered, you have a widget and then you try to apply a filter on it, and then backdrop filter is the one that gets tricky. This is where Flutter gets a little bit of a backlash, because whenever someone starts using backdrop filter here and there, they start seeing problems where performance drops or frames starts to be missing. Obviously, that is very clear. They tell you that in the documentation, because a backdrop filter is something where you have widgets and then you decide that you want to use the backdrop filter on a specific widget. It's not applying it on that specific widget only. It's going to have to go and get a copy of everything that's rendered behind it. So you can tell that one is very expensive and one is not. So the first thing that we have to take away from the difference between these two is that if you want to just blur something very specific and you can use image filter, then use it straight away. Don't even think twice. Backdrop filter, in the other hand, it has its useful cases, very specific use cases, but most people, they use it for everything related to blurring for some reason. Sometimes it ends up bleeding. Yes, for sure it ends up bleeding, because blurring is something that, especially when you have backdrop filter, you need to take a look at everything that was drawn behind. So it doesn't matter if you clip it or not, backdrop filter will bleed into the contents of or whatever is outside the clipped area is going to get inside the blurred one as well. So for both of these, we have to provide them with an image filter, which is an operation that happens to apply on a raster image. Remember, rasterization from the GPU pipeline. So this is happening at a level where everything has been built, layouted, and then painted. So everything has happened to the image. Now we have the image in a format that is like a bitmap. So we know how, or at least in Flutter terms, raster image is UI.image. It's not an image like something that needs to be decoded or whatever. It's decoded and already ready to be painted. So now that is the normal image filter that we know about, but also there is another one called color filter. So for backdrop filter, for example, we usually just use it for blurring, but we can use other effects from the image filter class and also from the color filter class. So for that, I'm going to show you a couple of these. Sorry, just to make sure we know what's possible with other image filters, which is obviously color filters as well. So yeah, I tried at the beginning trying to spell how to say the name of this dish, but I don't think I can do it. If I do it, please don't. Paella. Is that right?
Paella,
no?
paella. Paella.
Okay, yes, paella, whatever he said. But yeah, it was a good example to showcase the different kinds of color filter. So all of these, obviously, you can use them with backdrop filter and image filtered as well. This one here, this example here works really well because it tells you exactly what you need them and what you need them for. So here, for example, we know So it's like you have two images. So you have the image that you want to apply the filter on. Let's say it's the image of the dish here, but then you want to apply a color on top of it. You want to apply a color filter on top of it. So the source is the color. The destination is the child widget that we have there. You can see some of them, they look very, very much the same. Some of them produce really nice effects that we can start to think about easy ways of using them. It starts to get interesting even more when we start changing the opacity of the source color. So here, for example, when we say source in, it keeps the image with or like just the shape of the image, and it fills all the details with the source color, while source out is obviously going to do totally the inverse of that. We have other ones where they combine the two, so it applies like some sort of a layer on top of the image, but obviously it doesn't go beyond the edges of the image. Some of them are really good for coloring. For example, if you want to unify how the images look, so let me say I want this yellow, and then I think the best one here, especially when you want to unify how most of your images look like, and you obviously know that all of these images are going to look very much the same. Something like multiply or hue, they really make the difference between the images a little bit less clear, and especially when you have a scrolling list of images and you want them all to feel like they are unified. But apart from that, obviously this demo here is just as a way for us to understand what kind of filters are there and what can they make in the end. Obviously, they have others, so we can do some other color corrections. So here it's the same image and it's the same result. They just do some other color corrections that I really have no clue about, but this is what they do. The matrix one is the one where we get to choose the values. It's not just the values of the colors, but it's all of these. You have to make sure. I have to make sure that the soft light or blend modes, they do not make any difference. It's just for the demo, but they are all being applied within one blend mode. Yeah, so those are all the modes. It hopefully helps you, probably if you look at the demo even in details, to see and understand the difference between them. But that was for color filter. Now we know you can use color filter in a backdrop filter or image filter. The other one is the more interesting one, obviously, which is the class image filters. That's how we use blur. But we have others. It's not always just blur. We have dilate, erode. We have another one for matrix. We don't know what does that do. And we have one for composing multiple ones. So let's see what we can do with all of that. If we play a little bit with an image, with a main image filter, like we can already see multiple things that can be done. So we can blur on one axis, for example, on the x-axis. We can blur on other axis. Obviously, why it is important that we know that we can apply only on one axis instead of both. We can use this, for example, to create something like a motion blur. If we apply, for example, only on the y-axis and then we animate it, it's going to produce a really nice motion blur. But most of the time it's being used in a combination so that we blur the content right away. Other features that they have there is the tile mode. The tile mode for something like blurring, and you already can notice that blurring is expanding the size of the bounds, which is one other difference between that and the color filters. Color filters, they do not go beyond their bounds. They always stick to their bounds. They just are linear operation, while this one is a bit more complex and it does go beyond its initial bounds. So what are the different kind of tile clamps? Different tile modes. So you have repeated. So you will start to see the difference if I make it a little bit larger. So repeated is going to take the same image, repeat it multiple times, so that when we go at the edge of the blurring and we are trying to blur something, we know, like, if at least if we don't have anything beyond that, what do we do? So repeated is going to repeat the image. Mirror is going to mirror it. As you can see, it's nicer. The only one that is very interesting and can take us to something close to what we have seen with MKBHD app is the decal one. It doesn't clip it into a rectangular area. It actually starts to have smooth edges because it says at the edge, do not take the color from any other source, just make it transparent or blend it very nicely with the edges. So that is everything you can do with the image filter API. But as we have seen, we can compose it with other things. So if I disable the blur and then just play with other effects such as dilate, you can see that dilate is into the details of the image. It tries to, for example, make anything within very visible borders. It tries to make them bigger. So it does something called edge detection, which is some sort of convolution method in image filtering. You go into the edges, and if there is an edge, try to make it bigger. And then we have erode. So erode, it does exactly the opposite of that. So if we are at an edge, try to make that edge very, very much smaller, so that now we see that the areas that they have no visible edges, they are becoming the dominant part, while dilate does the opposite of that. And probably you can see where this is going. Like, we can use this combined with another type of blur, and then we switch between which one is first, but because we can decide which one is the first one we apply, whether it is erode or dilate. But as you can see, it's making a really nice lens blur effect, and we know for sure that Flutter doesn't support lens blur or anything close to it. It just supports normal blur called Gaussian blur. But now with composing, with the compose API, or just composing two image filters, we can get a really nice lens blur like this. Obviously, we can use it to do other things. For example, with shader mask, we can use it to create that smooth edge because we are applying the blur on a specific area. That area is defined by, let's say, a gradient. So here, I'm just going to increase the gradient, the blur sigma, and then we're going to play with the gradient stops. So this is allowing us to do something as close to that smooth edge as possible. One more very interesting one is the saturated one, because on this one we are combining image filter with color filter. Both of them are image filters, but from this new knowledge that we have acquired, which is the fact that we can use color filters and combine them as we want. You can see here, if I'm gonna try to show you a little bit more clearly, I'm trying to blur the up bar or the content behind the up bar, and on iOS by default they don't just blur the content, they always add saturation. And that saturation differentiates when we are in light mode or in dark mode, so that the content is highlighted a little bit more and the contrast is even better, so that you can read it in a much easier way. So I have here the dark preset. So in a dark theme, this is how it should look like. And then on a light theme, this is how it should look like. So as you can tell, the content behind is being saturated, and that is obviously done through using color filters as the inner filter, and the blur as being the outer one. And we can take it further, obviously, but these presets define very, very nice light and dark themes that we can use. And now I think we have seen enough about what we can do. We have tried to customize it by using the available APIs, but the question is, how can we customize it even more? on a level where we can control all of this logic, because right here we are just like playing with Legos, like we are trying to put this part with this part and trying to make something in the end work, and hopefully it works. We are not deciding or writing the logic of how all of that is working. So to understand anything or try to customize anything, we have to understand how it works behind the scenes. So here I have this really nice image of Mario to help us explain how blur effect works. So here, if I'm trying to blur one single pixel, what do? I go to that pixel, I look at the pixel's neighbor in that pixel, I add them all up, and then try to divide them by the number or the size of the kernel. So in the end, I'm going to have a smoothed out version. That version of the color is the combination of all the neighboring colors. And the blur intensity depends on how big that kernel is. So if we make the kernel a little bit bigger, it will reset all, and then I'll make the kernel a little bit like the size of 5. You can probably tell that the final version is more smoothed out. So if I try to blur all the pixels one by one, this is how it looks like with a kernel size of 5. And if I take it back to 3, this is how it looks like. It's more close to the original image, but it is still blurred. What you can see here as well is the number of operations: sampling, multiplying, summing, and dividing. If we are increasing it from 3 to 5, you can see that that number is not just going in a linear way, it's going in actually an n of 2, or an n squared, sorry. So it is very performance. So it takes a lot of performance to do such a thing. That's why blurring is very complicated. And one other thing is in Figma, for example, when you take any image from Figma, they give you blur radius, and then you want to do it in Flutter. You take the value from Figma, which says, oh yeah, blur radius of 35, and then you want to go to Flutter and apply that the same as a Sigma. Obviously, that's not right, because Sigma and radius are totally different things. For the radius of 3, the Sigma will probably be close to 2.2, and then the value obviously is not linear after that. It starts to get smaller and smaller. The Sigma is always smaller. So try to find the value that looks right instead of taking the one from Figma straight away. That's just one little thing I wanted to mention here. And as you can see, the bigger the radius is, the bigger the kernel is. And you can imagine with a bigger kernel size, we are doing this for every single pixel. So if you have a large image, you are going to every single pixel doing this operation or multiple operation this number of times. So that is about the blurring. And now we know how it works, and we know the operation that needs to be done. Shall we do it in Dart? So this is using basically just a for loop. I'm reading the colors of each pixel individually, and I'm going to start with very small Sigma. I'm going to click apply, and as you can see, I hope my slides don't break if I go with a higher Sigma. So let's go very careful here. So another time, I guess, I hope you can see it. The application, all of the application has been frozen. This is because it's doing all of these operations in the CPU, and it's blocking the main thread that Flutter uses to draw anything into from widgets to anything else using the painting API. So to fix that, we need to use isolates. So with isolates, I can freely use different Sigmas as much as I want. So I can use a Sigma as high as 12. Obviously, you can see it took 7,770 milliseconds. And it worked. It really renders a really nice blurred image. But the problem is this number is nowhere close to that 16 milliseconds, or even if it's even less. Now we get with the newer devices, it's like 100 times bigger than that number. So we cannot rely on this to use it for creating real-time effects. We can use it for caching or offline rendering for other things, but it definitely is not a solution practically nowhere close to that for rendering anything related to blurring in real time. And that is obviously the main reason why shaders exist, because when we write the code, we are writing it to be running on the GPU. When we use shaders, while on the CPU, it's running in a way that is one method after the other. So the CPU cannot do one operation. Obviously, there is parallelism and threading, but it is very limited compared to the GPU. The GPU is made to do that. So, for example, if we get a fragment shader, and you imagine all of these as pixels in the code that I wrote in Flutter, I'm processing every single pixel one by one, and I cannot move to the next one before I finish this one. I can use threads, I can use anything else. I can use them to make it faster, but I cannot compete with the speed of a GPU that does parallelism, because this is what they are made of. So the speed is probably 10 times bigger. This is just in theory, but in practice, it's way faster. Well, that hopefully explains how the blur works and why is it a little bit expensive. Obviously, Flutter does it. It doesn't do it in Dart. We just go here into the API, and the API starting point is Dart. But after that, it definitely is not Dart. After that, we just send it to the C side in the engine, and then from the C side, it gets straight into fragment shaders. This is the fragment shaders that defines the logic for the most common blur, which is called Gaussian blur. It's based on that curve, which is called the Gaussian curve or the bell curve, because it's more natural than actually getting the values of the neighboring colors and multiplying and then dividing them. The Gaussian one, or the Gaussian distribution, is a bit more smooth. This is why it's also called the natural distribution, or it looks more natural. That's why Gaussian blur is used. And there are other reasons why it's used. For example, it's separable, so that we can do a lot of optimizations around if we, for example, if we want to do it only on one way or in two ways, we're going to reduce that kernel, the kernel size that we have seen. We're going to reduce it from being a 9 by 9, for example, to something as small as just 3, because of the nature of the separability of a Gaussian function. So that is one of the main reasons why it's used. But the important bit is being the Gaussian blur is very naturally nice looking compared to other blurs. But now going back to the issue that I have shown you at the beginning, which is the Marcus Brownie application, I still don't have a way to fix that with a current API in Flutter right away. But I realized that I can use multiple tricks and combine them to use like a gradient mask, because as I have shown you, like you can use a gradient mask to apply it on a picture. Then knowing how color filters and color blending works, we know exactly how to show an exact part of the image being blurred, just an exact part of an image that we want, which is the part where there is a gradient with color that is not transparent. Any color is there. So with that, obviously, I got deep into the problem, and they created this library called Soft Edge Blur. It seems to be now used by a lot of people, but it fixes the problem of that soft edge at the same time. For example, here in the Airbnb card, like as you can see here, there are multiple cases where I have used it, for example, to create a card like the Apple. I took this design from Apple App Store, and it's just a gradient that is really smooth, and obviously it's not like a whole new area of the UI, so it is still blending really nicely with the background. And there is the contrast where I can read the words app we love, Airbnb, discover a special home, and all of that without a problem. And it has a tint on this one. The tint is just the color I know about. Then the example where it's used in a music player, so that when I'm fading at the top, at the bottom, it doesn't just clip the content, it actually does progressively blur, or progressively applies the blur. It's not progressively blurring, it's like the value of the blur is still one or the same value across all the pixels, but it's progressively applying the gradient mask on top of it. And it can be used, for example, in maps as well to create a really nice edge there. But most importantly, I used it to recreate the same effect in the Marcus Brownlee application. So that was a success because it's I love the app, and that was one of the main reasons why I wanted to deep dive into that problem. Okay, now I guess we'll need to write some code. So let me drink some water. If you have any questions so far, please let me know. Or did you set up your what was that? Your coding machines, if you want to follow.
Questions?
Yeah, very great presentation. I really enjoyed it. One question that I have, you mentioned blur is happening on GPU using fragment shaders,
Yes.
which can become very, very super fast. Then my question comes in, why when we have dynamic blur, like when we have blur on scrolling content, like a list view, like a navigation bar or app bar, why it can affect the scrolling performance?
Well, yeah, that's a very good question. I guess I was about to mention something related to that, but the main problem with that is not the blur itself. Like, blur has been optimized a lot. Like, the Flutter team has spent literally 1 year of optimizing the blur so that it can actually render as fast as possible. Still, it's faster on iOS than it is than on Android. Still, there are Android devices that are so old, but Flutter runs on them where the performance will drop. Like, those are just like limitations that are very clear, because we know computationally, unless there is a new breakthrough algorithm to blur things, there won't be a way where you can reduce the amount of calculations. But that aside, Flutter specifically, in the case where you said when you're scrolling, so let's assume you wanna add that little nice app bar that is blurred behind. So for that, you have to use backdrop filter, and then you have another one at the bottom. So you have one for the up bar, and then one you have for the bottom bar. So both of these are going to be like two different backdrops. So the first backdrop is going to happen at some point where it says, okay, now I'm here, now try to find everything behind me, get me a raster of that, copy it, and then clip it. Obviously, clipping is by itself is an expensive operation, and then blur it. So the backdrop is the part that is expensive. The clipping might not be as expensive, but still is expensive. And then you have to do it all again at the bottom up bar, for example, and it will do all of this again. So it's not the blurring that it is expensive, but the use of backdrop, for example, in multiple places, and it is the same UI. For that, they have a PR that is still in draft mode, actually, as last as I have seen it, like 1 week ago, where they will allow you to specify in backdrop filter, like you specify the filter, you specify the blend mode and everything, but you will also specify an ID. So you will be able to give it a string, like a key, to say that whatever is on my UI is going to all share the same backdrop. So I don't really need to recreate it again. So this will actually improve the performance if you have multiple backdrops. Obviously, if you have only one, the only way to reduce or make the performance a little bit better is to use smaller sigmas. Like, just don't go wild on sigma. Like, there is a big difference, as we have seen, between going from like 10 to 50. Like, don't play with the sigma as just a value that is like a color or opacity. Like, those are totally different things. Like, going from 10 to 50 is a nightmare increase in number of operations. As I said, like the big O notation for this, like for the pixel itself, is n squared. They have been able to reduce it, obviously, using multiple tricks, but this is still a lot of computation. So to recap, yeah, if you have multiple backdrops, they might be the main reason for the scroll performance. The backdrop is an expensive widget, backdrop filter. If you can, for example, the way I have done it with this library here, I'm not actually using a backdrop filter at all. Like I'm using something like called GPU images to sample whatever the rasterized to get the rasterized version, and then I'm gonna have to clip the image, but I'm not using backdrop. So I don't. This is totally different from the way backdrop filter works. I don't have like benchmarks to compare the performance, but backdrop needs to know everything behind it, while this method here is being applied just the way image filter or image filtered widget is working. And as I said, the second bit about performance is if you can use a smaller sigma, try to use the smallest possible sigma with not to get in trouble. Like if the sigma 10 works, maybe a little bit worse than 50, then definitely use that one. Hopefully that made sense, but yeah. The performance issue is just because this is a computationally expensive operation in a scrolling environment with backdrop. It's not the main reason. The backdrop might be the main reason.
Perfect. Clear answer. Thanks.
Thank you. Okay, let's go write some code. I hope anyone is gonna share the pain with me, because I really don't want to write OpenGL shading language live. Anyway, so we have, okay, 30 minutes. So let's see what we can do within that 30, and then it's as quick as possible. So I have this is the only setup I have here for you. It's just the main app. Flutter app doesn't do anything. First thing I'm gonna do is I'm gonna add a folder called shaders. We're gonna replicate a very simple one, or first, at least let's start with first shader. You can give it the name, any name, but then the extension is going to be either GLSL, graphics, OpenGL graphics shading language, or you can use Frag, which is extension for Fragment Shader. I will use Frag because that's what the Flutter team uses. This language is very similar to C, so it's typed, and you have to, and it has even other weird rules because it's not fully like general purpose language. It's just for writing fragment shaders. So we're going to start with the main entry point, which is the main function that doesn't return anything. We said we want to return a color. So for that, we have to create a variable, and we give it, for example, the name frag color, which is the fragment color, the final color of the fragment. And the way that colors work here is using vectors. So that's the only possible way for us to declare variables here. So we're going to say vector that has 4 components. Why 4? A color is just 3, right? So red, green, blue. But then there is also the alpha. So we have to remember that. So the frag color is going to be a vector of 4 components. And let's create it right here. So we give it, let's say 0.5. So all of these values are normalized. So 0.5 or so is just like 255 is 1, and 0 is 0. So 0.5 is whatever in the middle. So 0.1, and then let's say 1 for the blue channel. And then obviously we want it to be fully visible. So this is our very first shader. It doesn't do much. It just tries to draw a color per pixel. The second thing we have to do is to go to PubSpec, where we usually add assets. Now we're going to add shaders. So they are treated the same way as assets, just because they need to be compiled by Flutter and transformed into another shading language that might work on whatever the target is, Metal on iOS, or OpenGLS on Android, or any other platform, for example, WebGL when we are targeting the web. So here we'll just say shaders first frag. Now we have everything ready. Let's go and do the Dart side. Let's call it first. It's going to be just a stateful widget. Call it first shader. Everything is so big on my screen. I can see the pixels in my I can see the pixels in the word. Anyway, so we have first shaders, and what do we want to do with that? We obviously want to load it. It's asynchronously loaded, so let's do an init state, call it load shader, and this function load shader is going to do something with fragment program. Fragment program is the API for us to load shaders, so we know the file, where is it stored, and now we're gonna load it, call it, let's say final, let's call it fragment program. It's this part where we do the asynchronous operation. We can do this outside of the widget tree. We can load all of our shaders at the start of the application if we want to not wait or show any loading indicators to the users. But for us now, let's call it shader. It's going to be a fragment shader. It's going to be null at some point, so let's make it nullable and provide the value here. First thing is we check, because as I said, it's asynchronous, so it can be null at some point. If it's null, then let's just return circular progress indicator. If it's not, then we are going to draw this shader. How do we do that? We can access it through the Canvas API, so anywhere where you have a canvas. And the easiest way for us to access a canvas is usually through a custom paint widget. It's going to have a painter. Let's call it shader painter. Creative name, shader painter. And create this class here. Let's make sure everything is looking fine here. The size, let's give it size 200 by 300. 300. And shader painter is going to be a class that extends custom painter. Two missing classes. I'm not going to care about the should repaint for now. I'm just going to return true so that we have a very easy productive session. And then we're going to access the canvas. So canvas, we can use, for example, draw rectangle. So if we want to draw a rectangle, I'll specify that later on. And then we have a paint object. The paint object is where we specify the shader. So if I create the paint object, a very basic one, and then here it asks me for a shader. The shader can be other kinds of shaders, because Flutter is as we have seen, we just now have the possibility of doing custom fragment shaders. It does not mean that Flutter was not using them or anything, because as we have seen, they are fundamental to any graphics related programming. So let's keep it there. Let's create the rect for now. Let's create the rect from left top width 0, 0. The width is going to be the whole width of whatever we are providing, and the height is going to be size dot height, whatever the final size is that. And for the shader, we are going to provide it in the constructor as a fragment shader. Definitely is not going to be null, because we know that at that point is not going to be null. Now this shader, we're going to provide it to the paint object. Now we have done that. Let's provide it to the shader itself here. Here, make sure they know it's not null. Okay, well, I'm just gonna run the application. I really don't know what to expect so far. I'll have to remember. But the main thing is I need to say that I'm rendering this application. Well, it draws a color. I'm assuming that that color is coming from here, because otherwise, why we have a random color like this? Let's see, 2, 1. All right, well, it's coming from the fragment shader, so that's a success. Obviously, it's drawing it all over the place. We have defined the size, but it's taken the size of the constraint, so it's coming from the top. Let's make sure it's at the center so that it draws only that size. And now let's take this a little bit further. Let's try to send the values of the color from the Flutter side. So for that, we need inputs. Inputs here are called uniforms. So to define a uniform, we just use the keyword uniform. We define its type. So it's going to be vector3 because we just want to give it the RGB values. We don't want to. We want it to be always visible, no transparency changes. Let's call it color, or uColor, as a way of saying that this is a uniform. And then here, one thing you need to know that is really nice about GLSL is that it has something called swizzling. So for example, here I can create vector4 from only one component. Obviously, it's not going to look nice. Let's give it another color, for example, and I don't know, it's not working right away. Okay, it's working. So here what it is doing is just assigning the value 0.5 to all of the other components, including the transparency one. Now I'm going to take that uniform back again, and I'm going to put it here in a vector4, and I can say the components, each one of them, obviously it can be R, and then red, then green, and then blue, and then the transparency is going to be at 1. But as I said, there is even a better way to do that. Thanks to the swizzling feature, we can just say uColor. It's going to take the first 3 components of the vector3, and then we only apply the fourth one manually. So now we have the uniforms. How do we pass the value of these uniforms from the Flutter side? So we go into the shader, and then there is a very simple one called set float, which is to set the value of one uniform. We have to provide a hard-coded value for the index. The value is going to be, as I said, something between 0 and 1 because it has to be normalized. That's the way they work in fragment shaders. So if we are trying to define our color as, let's say, colors.yellow, if the color is yellow, let's say yellow accent, we're going to have to send each of the values red, green, blue, because we want to send it in 4 components, but we have to divide it by 255 so that it can be normalized. So red, green, blue, and give them the right indexes. You will see that the API is very low level, otherwise we will not be getting these random issues that the indexes are not valid. So 0, 1, 2, and then yellow, red. Well, I'm just sending the red channel, so let me send the green, then the blue, and Tara, we have the yellow color. So now we have seen how to send uniform values into our program. Let me double check what do I have other cases that I wanted to show. So we have the color one, and I guess now it's a good time to do another filter that I talked to Ahmed about. Wanted to tell him to do it just because I saw when he announced this workshop, he did a really nice work on the art. He or whoever did that as well, I appreciated that. So I wanted to do something to recreate it, which is using like a pixelation shader. So a shader that does pixelate the image. But it's just our transition into something else, which is, as you can see, these shaders that we have created so far are only doing one thing, which is drawing a color into the space or drawing something solid into the space. The next thing we can do is to take an image and transform it. Image filters, right? Pixelate. So pixelate the track. Let me see, what do I have for that? Well, I'm not going to try to create the whole thing again. So shader starter, this is doing everything as we have done it from before. just a simple one. What am I including is just a couple of other headers. So here to decide the precision and then the version of GLSL that we are using. And here, the important bit is I'm including some other values that are coming from the Flutter side. So all of them are in a file called runtime effect GLSL. You can take a look at this file. I don't think I can access straight away from here from the editor, but you can take a look and see all the other functions that are available there. So how do I do the pixelate one? So if I try to start from the Dart side, maybe it will be easier for me. Pixelate. So stateful pixelate demo. So pixelate demo is going to look like this. We're going to have an image, Flutter logo, and we're going to provide it with a font size of, let's say, 70, so that it looks big. That's all I need from the image for now. Let's make sure it's the one we will be displaying as a demo. Okay, so it's showing. Maybe just add the material widget so that we are not doing everything in a blank space, as Taylor Swift said. Okay, so now we want this image, which is just a Flutter logo. You can pretend that this is any other widget, an image from the internet using image.network, any other kind of a widget you can think of here, apart from platform widgets. They are the exception. They always have been. And for doing that, I'm really not going to do the hardcore stuff because it's going to take a while. So for that, there is this very practical library called Flutter Shaders. I have already added it here, but it's a very high-level API, so that it just has some of the details that we were doing. So it makes it just a little bit easier to use shaders, but it doesn't really do a lot of other technicalities, apart from one, which is how to take a widget and turn it into a rasterized image that we can provide to the shader. So that is a widget called animated sampler, and then we'll take a look at that one right now. So first thing is we want to turn this Flutter logo into something we can use or pass as a UI image, because that's what the shaders will understand. So there is a widget called animated sampler for that. It has a builder and a child. So let's say the child is the logo, the builder, whatever the API for that is. Let's take a look. Well, let's just copy all of this. This is the header of it. As you can see, it takes an image, which has to be a UI image, the size, and then the canvas size. And now I'm assuming this shouldn't be complaining unless we are in a const scope. So get it back to where it was. Animated sampler is going to provide us with an image, size, canvas. So to understand what this widget does very simply, I'm just going to use the canvas to draw an image. The image is going to be the one we provided there. We will start at the 0 position, and then the paint object is going to be the simplest one, just the constructed one. This somehow should draw that image. If it's not, there is another issue that we need to fix. Well, we don't need a shader here. Maybe we need to define the size of the canvas. But okay, well, let's ignore that for a bit right now, because I don't want to. The main point here is that the canvas draw image should draw that image now, but it has transformed it from being a widget into something that was rasterized and put into the GPU and then converted back into a UI image that we can use. And the second bit is that this library Flutter Shaders provide is a widget called Shader Builder. So it just does what we did, which is loading the shader based on an asset that was provided to it. So it also has a builder with a really weird callback. I don't remember all of these callbacks. So the widget is going to be the child. This is going to be the shader. And this is going to be the context. And here we'll be returning animated sampler. So animated sampler, here we provide you with what you require. Shader builder is asking us for an asset key. This is where we say the shader pixelate again. Make sure give it the right stuff here. Now we have access to the Canvas API right away. So let's draw a rectangle that's going to be the full size. Paint. Object. So the paint object, we will just pass the shader, which this time is just coming from here from the shader builder, and then we will pass it a couple of values. But for now, we'll pass it the most important one, which is a uniform that defines the image. Here, this is complaining about something. Yeah, the size of the editor is so big that it really can only see one way or the other. But yeah, we'll deal with that. So now we want to pass something to the shader. We usually pass using set float or set other values, but we want to use specifically image sampler because it's the only one that accepts an image, and they start at a different index. So if you have multiple uniforms and one of them is the image, the images are always also going to start from 0. As I said, it's a very low-level API. The library tries to help with that, but I want to make sure we understand the low-level API since we are doing very first time look at this. So the value, we don't need a uniform for an input value, but we want one for the image. So uniform is going to be called like sampler 2D, and let's call it uniform content. So what does this here do? Let me show you real quick. What is it called? I'm switching between Dart and GLSL. I used Final. Final is not going to be here anytime soon. So uContent is going to be the image, but we want to access its values. So image color, let's call it image color. We need to use a function called texture. Texture is a way of saying go to a specific place in a specific texture and give me the color of that one. So here we know which texture we want to get the value from. So uContent, but then we will need to specify the coordinates. Coordinates here are in a UV system. Why UV system? U is like on the horizontal axis, V on the vertical axis, unless I'm totally wrong. But why UV instead of XY is because XY has been already used. This shaders were like mainly for 3D programming and all of that. We can use them on 3D obviously, but because the systems are already using XYZ for 3D, UV is when you map that into the 2D world here. So UV is just like a way of saying this is our way of naming the coordinates in a 2D world. And let's define them. Vector 2 UV. So for that's why we imported runtime effect. We'll need to use something called Flutter frag chord, which gives us the coordinates. Flutter provides them. So instead of us providing all of these values in uniforms, Flutter is going to provide us with those values. What we need as another uniform, which I missed, is the full size of the view. So it's going to be a vector 2. Let's call it U size. Then we divide it by U size. U size is going to be something I have to pass in a little bit from here. So set float is going to be a value that is the size. First we start with the width and then we do the height. 0, 1. Obviously, as I said, for floats or any other uniforms, we start from 0, 1, 2, 3. But then if we go to samplers, we have to start again from 0. So pixelate, hopefully it's doing what it is doing, and then we'll try to render the image color as the final color. Let's see what is this complaining about. Index out of bounds. So I have the uniform, which is vector. I have the sampler, vector 2. Okay, maybe it's one of those issues that, well, usually when these issues happen, I have to restart, but I don't want to restart, so let me do this real quick. Width, height, send them as floats. 0, 1. Well, I'll try to restart it, check out my notes, and then see if that helps. Pixelate.
Does it have to do because we use the 0 twice, or we can use the 0 twice as an index for the set float and the set image sampler?
We have to use the index different. We restart the indexes when we start using samplers. Samplers is the only exception. For floats, it's floats or any other. I mean vectors. There is nothing like set vector. So if you have a vector components of 2, then you have to pass 0, 1. So if you have vector 1 as the uniform and then vector 2. So if you have 2 vectors, the first one is vector 2, the second one is vector 3, you have 5 components. So you have to go 0, 1, 2 until 4. Let's see if it's still complaining about it. Yes, it is. Why is that? That is very unknown to me. So we go pixelate, float, uniform sampler 2D, content out of bounds.
We're not using width and height.
Oh yeah, I'm not using that, Raj, for sure. That's one. I should have complained about that at a different stage though. Index out of bounds. Let's see, is it complaining about this one? Maybe I'll just be zooming out for a second or two so I can actually read. Well, in my demo here, it really is just 0 set image sampler is looking fine. Well, I guess we can go to the version that actually works. I don't think that's cheating, but it will. It's the same code, guys. Trust me, it's the same code. If it's not, check it out here. Okay, it's the same code. Okay, I'm not cheating. It's just very flaky API. Okay, let's restart this and hope that the flakiness of this is going to go away.
Live team was always go bad.
Yeah, I mean, I decided to do this so that it will be entertaining for you.
That works.
Yeah, this is exactly one of those issues that they just happen and then they get stuck for some reason. And I always fix this by restarting it. I guess I'll need to report an issue at some point. Oh, that's it's a bit sad. So let me see if another one is going to work, or is it going to be just that? It's being okay. Well, if that doesn't work, we have even better. But you already know the pixelate. The shader itself is very simple. Like I wanted to get you to the point where I explain the shader, but mainly we just have to define the pixel size. Because now we are taking the picture, the original image, and then we try to pixelate it. So we define the first thing, which is the pixel size, which is after the image has been pixelated, what will be the size of each pixel. And then we use that as a way of defining the bounds. We try to we scale the image up so that we can take the colors from the scaled image, and then we scale it back. Here we can use round, seal, or any other function that is used for rounding to get the nearest color instead of getting the color itself. So the entire pixelation code is, so this will draw the original image. If we do it like this, it will draw the original image. Like this, it will draw a pixelated version of it. So by the end here, you will realize that a lot of math is involved here. So this math, it's not like we are writing straight away logic, which is like for loops and if conditions. We can use that, and we will be using that in other places. But using math and linear algebra here is the only way where you can optimize. So if you can do so, there will be other examples where you can see that the use of linear interpolation is much faster than using an if condition. And obviously you can do a simple if condition to check whether something is true or false, but if you use something like a linear interpolation, you do not get a true or false right away, but you get a smoothed out version of anything that you want. But let's see, this demo here hopefully is working. Yeah, so this one is working. I think we're gonna get back to this one. Since I'm looking at the time, I'm gonna make sure I'm not gonna run over all of you here by taking all of your time. But these are other examples of shaders that I'm gonna all be sharing with you so that you can take a look at. This is a really nice gradient background that you can use for music applications. For example, this one here is just a gradient mixed with other gradients. It's not a mesh gradient, but it looks very nice. Another one is called the chaos button. I have seen this demo on Twitter. You can see the API for this one is very similar to the ink, the one we have seen for Android 12, which is the ink sparkle one, but instead of ink sparkle, there is this much better effect. This obviously doesn't work with all applications. It has to be very specific up where you want to have an Easter egg or something. This is how it looks in Flutter, and you can modify all of that. Another example is this demo that was shown on iOS 17, was it iOS 17? Yeah, iOS 17 on WWDC this year, where they showed like how you can make custom effects. And this was one of the effects that they have shown. Because it was in metal, it was easily portable to GLSL. So I did that within the same day, tried to show that it can be done in Flutter as well. And it's a really nice effect for anyone to use. Again, buttons, I did this one. This one is a Galaxy button, so you can see that this might be useful in websites or desktop ones because it just has an anticipation feel to it. You have the button and it's moving, you don't know what's going on, but you really want to see what happens when you hover over it. But then you see, oh, this is amazing, I want to click on it. So it's like a clickbaity button, but it's a really nice clickbaity button. And this other demo here I have for you, I have made this one, it went viral, but I think the way I will show you this demo today is by showing it to you in an app instead. So I have made this very simple example application here where you have two phones next to each other and then they get close and something should happen, like as an effect. It's called the iOS share or a name drop effect. So if we toggle the animation, don't tell me it's not working as well. Wait, that's Android. Well, this feature is on iOS only, so that's why it's not working. Just kidding. It's all Flutter, so it works on Android, iOS, anywhere else. It's just think. Oh, this is very slow. So it's. I just wanted to make sure it's very clear to all of us happening here. So it's not as slow as I want it to be, but hopefully it makes sense. You can obviously make it faster. That is the effect that I wanted to show here. It's the same one in the video. So I can quickly move on to the next one. This is the one where I got most people to use it, most practical one. I hope you do not hear that noise, but it's when you want to remove an item from the list, instead of just boringly swiping it to the left or to the right, you can do a 3D effect. This is possible just because of fragment shaders. You can imagine a lot of transformation happening here and there in order to simulate such a thing. But the most important bit, it looks realistic, it's super fast, and people love it. The audio is just an addition. This example is frozen and then frozen a card. So why just say the card is frozen when you can literally freeze it and unfreeze it? So that's another case. I'm not sure why I'm talking when I'm not showing you the demo in highest details. Yeah, this is the freezing again, and you can unfreeze it in a nicer way. This one is shadow on non-rectangular shapes. You can tell, maybe if you have tried to do any kind of shadowing before, you know that you can do it only in low-level APIs. Like you're drawing a line, you can do a shadow. You are drawing a rectangle, you can do a shadow, circle, shadow. But if it goes beyond that, it will be impossible to create a shadow easily. There are ways where you can use color filters. As we have seen, you recolor the image, all of it, using a specific blend mode, but that is duplication. This one here is using a shader. It might be even faster, but no benchmarks here. It's just possible. Random experiments. This was just an effect when you switch between the pages. It just does a little bit of a nicer distortion effect. This one is really, as you can see, the background here looks very realistic, and it's not a PNG, it's not an SVG or anything. It's all made within the shader. So one very small mathematical function produced this high quality details texture, and it reminds me of the main reason why shaders are so popular in the gaming world. Like for them, it's about producing because games are super big, they don't really want to have a lot of assets, and fragment shaders and using mathematical functions to produce textures is one of the best ways to optimize and create something that feels realistic while not using a lot of assets for that. This is, I don't think it's showing up properly here, but it is just trying to bring the iOS app into Android, or at least just one page of it in the weather application, where they have really nice snow behind. So I wanted to bring that. So it's the shader part is the snow behind. This one is how you can, we have already seen how you can get the color of a pixel using the texture function. And this one here is using four textures. So it's only 4 textures, and you can use it to create a nice background from a specific image so that you can smoothly move to the next one. If the pixelation one worked, we would have shown you how to take it to the next level and make something like Instagram, where if you take a look at the profile picture of someone, it's not, the background is not blurred, but it's pixelated and then blurred. So you can do that, such a thing with the shaders as well. One of the questions mentioned something related to this as well, about not being why are there performance backdrops when you are like doing something like an up bar or a bottom up bar when you're scrolling, and then you have blurred content. As I said, the algorithm itself, in order to render such a nice blur, you have to find other ways or breakthroughs in order to make it faster. But if your main use case is just to blur the content behind it, but not specifically using a Gaussian blur, then you can use other kinds of blur. There are obviously other kinds of blur. They do not have the same final great look of a Gaussian blur, but they can look nicer in different applications, and they are obviously faster than a Gaussian blur. Not specifically any one of these here, but for example, the glass one is just makes a lot of distortion. It makes a lot of noise. It hides the details, which is the job of a blur effect, but it uses way less sigma and way less blur radius, if that makes sense. Blurs all over the place is the thing that is mainly where you want to use image filters. As we have seen, the world is not just Gaussian blur, there are other kinds of blurs. Stretch effect, the one we have seen at the beginning, is the one that I wanted to make the most. So let me go back real quick here to show you that one before I finish. So as I said on Android, so that's why I have this demo here. So right now on Android, if you scroll, you can see that it is scrolling in a uniform way. Everything is getting the same value. If I enable the shader one, you will see that it's uniform. It's a little bit larger. That is why I want to fix it right away. I have a lot of code for this one, but the only important bit is in the shader, which is all happening in one place. Let me just figure that place is it the demo one? Yeah, it's the demo one here. So a new widget called custom stretch over scroll indicator. It's literally the same widget that is inside Flutter code that uses the transform widget to change the current one. But this time I am using it in a way that I can use the shader instead. So here at pull layer, I'm just using animated sampler to take a look at the content and then transform it into a widget, and then I send the over scroll values and all of that. If I go here to the custom scroll one and then enable this specific one that I have made. So when I scroll, you can see that this one scrolls a lot at the top and with lower values at the bottom. It's very close to where we want to get this, and it proves the point that we can use this to fix that issue. But more importantly, because Android is open source, we can literally just go ahead and find the code of the stretch effect in Android open source, and it is in another language called Skia shading language, SKLSL. It's very close to GLSL as well. So I took that away and I tried to transform it into Flutter, and that's where I ended up with here. I hope that I have the code of all of that in one place. I have a lot of files in this demo. So I'm just gonna comment that code to show you the final version that uses the Android one, just as a proof of that we can do a lot of practical stuff with it. I mean, I have shown you a lot of examples already, but obviously this should be convincing you of the effectiveness of using blurs in real life scenarios. So here, this is the closest we will ever be getting to the Android one. I don't think I'm sending the right values, but it's using the same shader, the same shader that's in Android. It just literally took all the logic there from there. Probably I will need to change a little bit around the values that I'm sending, around what is considered over scrolling, but I guess that is a success for now. And that is the final problem that we wanted to fix. And now I want to skip these parts, go straight into the resources for tutorial learning. The first thing you want to do is, if you didn't pick up with me the first shader today, you can do the same by watching the video about custom fragment shaders at the Flutter Build Show. And there is a very well detailed documentation about fragment shaders. in Flutter, in the documentation, but most importantly, if you want to learn GLSL and the art of programming at the GPU, you want to take a look at the book of shaders, which is probably the best place to start reading about that. Another best place is a website I helped creating with Matt Carroll. It's called Flutter Shader. So if we take a look at the website right now, you will see that it has almost all the effects that they have shown you today, but in a way that is very, very accessible for you as a Flutter developer to just go take the code right away and put it into a shader that works. So for example, here, I'll just copy this code because it's not like Shader Toy, which is another place where they share shaders, but you cannot copy the code from Shader Toy straight into Flutter. But here, you can just take the code from here and then put it into the shaders file here. And obviously, you will have to send the right parameters based on whatever you want. This one has only 2 parameters, like the resolution. We know what is that. We have the time, which is the time that's passing. And it will create this really nice, for example, glitchy Spider-Man-y effecty. And there is a lot of other effects that you can take from here, others by other developers. It's not all the shaders here are by me, but you'll find many other examples from other creators. I hope I didn't bore you a lot, but if you got something today, I'm glad. And if you have a question, please let me know.